Welcome, welcome, welcome. Okay, good to go here. There's the usual attendance form. Go ahead and fill it out when you have a chance. So it sounds like everyone's classes are doing lots of things. It sounds like you guys are going in, unfortunately, very different directions currently, but it's all right. We can talk about all the things. Oh, you know what? Let me actually do one thing here real quick. Let me look at something. Okay, yeah, sure. 1 second. That's interesting. Why would you do it in that order? Huh. Sorry, I was looking at one thing. 1 sec. I just want to verify something. So if you guys have questions, you should definitely throw them out there. I'm happy to address them. Yeah, that's weird. Okay. All right. Wow, so many things to cover. Geez, where to start? Sure. We got volumes. Okay. Yeah, so we'll go ahead and start with some questions or some stuff from the kind of, I would say, the FAM side of things currently, talking about area and volume. But I do feel like we should do a couple of area ones before we jump into the volume one. So let's find some area between curves. And I've got a couple of them down here. Yeah, all right. So between these two curves, f of x equal to, yeah, that'll be fine, x minus 3 and g of x equal to x minus 3 squared. Squared, yeah, that'll be fine. So if you're trying to find the area between two curves, you first have to figure out, and then they don't give you any kind of like between x equals this and x equals that, then you kind of just have to set them equal to each other and see where they intersect. So we're going to set x minus 3 equal to x minus 3 squared. Sorry, I'm trying to figure out which of my pens are good. I should just start throwing those on the floor that aren't good. There's a couple ways you could solve this equation. I'm noticing that you've got an x minus 3 above these. You could just multiply it out, right? You could say, okay, x minus 3 equals x squared minus 6x plus 9, and then subtract x and add 3. So you get 0 equals x squared minus 6x minus x is minus 7x, and add 3, you get plus 12, and this does factor. You get x minus 4 times x minus 3. Those multiply to 12 and half negative 7. So you get x equal to 4 and x equal to 3. Now, if we look back at the beginning equation, you actually might have been able to guess that, because if you've got something squared equal to the same something, this has to be either 0 or 1. If x is 3, you get 0 equals 0 squared. If x is 4, you get 1 equals 1 squared. So you could have also probably figured it out that way, but this works just fine. Yeah, we could have seen, oh yeah, x minus 3 equals 0, or x minus 3 equals 1. It's another way we could have gotten there. So now that we have where these functions intersect, we can kind of, we could draw it if we wanted to, it's not necessary. We know we're going to find the area by doing the integral from 3 to 4 of the top function minus the bottom function. So which one's the top and which one's the bottom? Well, to find that, you have to pick a number between 3 and 4 and see which function's bigger. So I'm going to pick, unfortunately, 3 and 4, we don't have an integer between this. I'm going to pick 3.5. I plug in 3.5 here. f of 3.5 is going to be 3.5 minus 3, which is just 0.5. G of 3.5 is going to be 3.5 minus 3, which is 0.5 squared. And 0.5 squared is actually smaller, right? That's a quarter. So in this particular problem, in this particular interval, the f function x minus 3 is the bigger one. So we're going to find the area here is by doing the interval from 3 to 4 of this function, the top function, x minus 3, minus this bottom function, x minus 3 squared. Yes. And then you would multiply it out, simplify, right? You could do a u sub here. It's really, in this case, it's so straightforward to just multiply it out. You should just multiply it out. Now let's go to the other side here. So I multiplied that, right? That's x minus 3 squared is x squared minus 6x plus 9. And then simplifying, I like to simplify my integrand. So let's see, I'm going to have, let's see here, minus x squared plus 6x plus x is plus 7x, and minus 9 minus 3 is minus 12. And then we're just going to do the usual sort of thing. We're going to integrate. Antiderivative of that is minus x cubed over 3. Antiderivative of that is 7x squared over 2. Antiderivative of that is minus 12x between 3 and 4. And then the rest of this is kind of a pain. You're plugging in 3 and 4, just dropping heads everywhere. It's kind of gross. So you're going to get minus 4 cubed over 3 plus 7 times 4 squared over 2 minus 12 times 4, which is 48, minus, and then we plug in 3. The nice thing about plugging 3 here is that one of the 3's will cancel, so minus 3 cubed over 3 is just minus 3 squared, or minus 9. 7 times 3 squared is 7 times 9 over 2, and minus 12 times 3 is going to be minus 36. And then we want to put this all together, which is not everyone's favorite part of doing this, but we could. So you're going to get minus 64 thirds. 16 and 2 cancel to leave you with an 8 there. 7 times 8 is 56. 48. And we distribute the minus sign to each of these terms. So let's see, you're going to get plus 9. You're going to get minus 63 over 2. You're going to get plus 36. And then we can, I mean, this is where I would probably use a calculator. But if I wasn't using a calculator, this pen's probably trash too. Going through all the blue pens here, see if they're trash or not. Let's see, we're going to get 56 minus 8, 48 is 8, plus 9 is 17, plus 36 is 17 plus 36 is 53. And then I still got minus 64 thirds minus 64 over 2. So then you probably have to get the common denominator of 6. So multiply this by 6 over 6, you get 318 over 6. Multiply this by 2 over 2, you get minus 128 over 6. Multiply this by 3 over 3, you get minus 192 over 6. And then you put it all together, and 318 minus 128 minus 192 is something. I don't know, let's see. 128 plus 192. 320. So you get, well, damn, you get a mistake. Because so just to point out, here's what I'm getting, right? It's a minus, it's a minus. So I'll make sure, yeah, it's a minus. Okay. So I made the error somewhere, and the reason I know I made an error is because I've got 318 minus 320 is negative 2 over 6, which is negative 1/3. And I know I made a mistake because my area should have been positive. And I did do the right function. This is the bigger function, so that's a bummer. It always sucks when you make a mistake because then you have to go back and fix it. Let's go back and check. So I've got negative x squared. I've got plus 7x. I've got minus 3. Minus 9 is minus 12. I have to differentiate it correctly. Yeah. I plugged in 4, I got minus 64. I got 7 times 16 over 2, 7 times 8 is 56. Minus 48, and I plugged in 3, and I got minus 27 over 3 is a minus 9. 7 times 9 over 2 is 63 over 2. Minus 36, okay. I distributed the minus sign, I got plus 9, I got minus 9, plus that. Let's see here. I'm not seeing it. Right, but this is 8. 8 plus 9 is 17. 17 plus 36 is 53. I've got my 53 there. Minus that, minus that. So I'm definitely making a mistake somehow. Also, I'm making a dumb mistake here. Oh, I see mistake. It's a close one. So here it is. This is minus 64 over 3, and this is 63 over 2. But somehow my 63 over 2 changed into a 64 over 2. So it's good to, right? So the lesson to be learned here, right, is if you see you're getting the wrong kind of answer, because you know it should be positive, you know you check the top function being positive, and go back and check your work. So this should have been 63 over 2, which means that I multiply this by 3 over 3. I don't get 192 over 6. I get 3 times 63 is 189. And when I put these together, it's a close call, but it comes out right. 128 plus 189 is, let's see, 7, 1, 1, 3, 317. And barely, just barely, I get 318 minus 317, 6 is going to be 1/6. So it's good to check your work. So questions about this?
Could you flip back to the front, please?
Totally.
Thanks.
So just as a reminder what we did, right? To find the area between these two curves, we set the functions equal to each other to figure out where they intersected. So we could have, although it's not necessary, we could have drawn a picture. Let's see. Just trying to think of where I want to draw this picture. I don't really need this piece anymore. So just to show you what this looks like, right? Y equals x minus 3, looks like that. Has an x-intercept of 3, a y-intercept of 3. And x minus 3 squared is an upward opening parabola with its vertex at 3. So it looks kind of like this. Where you're intersecting at 3, 0, and at 4, 1. And so we're finding the area in there. So that's what we did.
Why did you plug in the 3.5 and like at the
I plugged in 3.5 because, so here's the thing, if I had drawn the graph instead of plugging in 3.5, I would have known, oh look, seeing this graph, I can see that the top function is the line. So the top function is the line y equals x minus 3. And the bottom function is the parabola y equals x minus 3 squared. But I didn't want to graph it. So instead I said, well, I'm going to pick a point in between 4 and 3, because that's where they intersect. And I'm going to pick the point 3.5. And then I plug in 3.5 to see which of the functions is bigger. When I plug in 3.5 to the line, I get exactly 3.5 comma 0.5. Right, that y value there is 0.5. Whereas I plug in 3.5 to the parabola, I get a smaller value. I actually get 0.25 for the y value. And so doing that lets me see that this is the bigger function at that point, meaning it's the bigger function on the entire interval from 3 to 4. The short answer is it allows me to see which one is bigger without having to graph it. Other questions about this one?
If the function had been instead of a parabola like a cube one, do you add the two?
Let's do an example, because that's a good question. And so let's see, I have an example here. It's kind of boring, but whatever. So, sorry, I want to think of an example that's kind of interesting. We'll find the area between these two curves. F of x equal to, let me think for just 1 sec so I can make this not terrible. I'm gonna go back over here so I can think of a function that you guys can't see, so I want to give you all the clues right away. 1 minute, please. Sure, that'll be fine. 1 second. Need some space to work here. Sure, that'll be fine. Okay, so let's find the area between f of x equal to x cubed and g of x equal to, what did I do there? X squared plus 6x? Yeah, cool. All right, so same sort of idea. We're going to first find where these functions intersect. And you're totally right, they are going to intersect in more than 2 places. So we're going to set f of x equal to g of x. And let's see, so x cubed equal to x squared plus 6x. We're always going to bring everything to one side, unless it's a linear function, which it's not. So you got x cubed minus x squared minus 6x equal to 0. And then we're going to factor. I can definitely factor out an x. And I can factor further and get x times, let's see, x minus 3 times x plus 2. So here's where these intersect. They intersect at x equal to 0, x equal to 3, and x equal to negative 2. And so here's what we're thinking. If we write these in order, meaning negative 2, 0, 3, we're actually going to have to do 2 different integrals. We're going to have to do, whoops. I should unbutton this pocket. I'm going to put stuff back there. We have to do the integral from negative 2 to 0 of the top minus the bottom. And then we have to do the integral from 0 to 3 of the top minus the bottom. And the thing is, a lot of the time with these kinds of questions, the top and the bottom function change when you go from one interval to the other. So between negative 2 and 0, let's plug in negative 1 so we can see which of the functions is bigger. So if I look at f of negative 1, I get negative 1 cubed, which is just negative 1. If I look at g of negative 1, I get negative 1 squared plus 6 times negative 1, which is going to be, let's see, 1 minus 6 is negative 5. Which is bigger, f or g? Yeah. So we're going to do f minus g on that interval from negative 2 to 0. On the other hand, so here's the thing, they don't always switch. Sometimes it's still the same one that's bigger, so you actually have to check. You can't just assume it's going to be g minus f for the other one. So now from 0 to 3, we're going to check a point between them. Not the end point, you have to check one of the in-between points. I'm going to either plug in 1 or plug in 2. Either way will show us. See, f of 1 is 1, g of 1 is 1 plus 6, which is 7. Or we could have checked 2, right? F of 2 is 2 cubed, which is 8. G of 2 is 2 squared plus 6 times 2, which is 4 plus 12, which is 16. Either way, we're either picking 1 or 2 between 0 and 3, or you could pick something worse like 2.5 or 1.5 or whatever. You still see that g is the bigger function. This one's going to be g minus f. So the way we're going to find the total area between these two functions is to do this integral plus this integral. So let's go ahead and look at the other side. I'm not going to draw it too just so you guys can actually see that, but I want to set it up first. So Hopefully those of you that had a midterm recently, it didn't go too terribly. Have you guys gotten your grades back yet? I mean, I can take a little while to grade test, so maybe you did. Oh, you did? Okay, good. Well, if you have questions about your midterm that you want to ask me, like if you want to like send me an email and say, I'm curious about this, you're welcome to. And I'll try to help. Here's the attendance form again, in case you guys didn't get it yet. So let's see, we were doing this problem. So we're doing, it was the integral from -2 to 0 of f minus g. And again, f was the cubic function. And g was x squared plus 6x. Plus the integral from 0 to 3 of g minus f. And here's what this looks like. So if we graph this, my graph is not going to be super excellent here. You know what? This is an excellent time to use Desmos. Why am I trying to draw things that someone else can draw much better? So let me pull up Desmos real quick and let's see. Sorry, 1 second. Yeah, Desmos is great. You should use it. I like it. I should share my screen too. Sorry, sharing the screen. So let's see, we can graph both these things. So here's x cubed. That's not a cube, there we go. And the other one was x squared plus 6x. And then we can see from -2, right? From -2 right there, they intersect at -2, -8 to 0. The function, the red function, which was f, is the bigger function than the blue function. And then from, if we zoom out a little bit, from 0 to 3, we can see that the larger function is the blue function, x squared plus 6x, and the smaller function is the cubic function, x cubed. So that's how I mean, we don't have to draw them to be able to know which one's bigger. We can definitely do the thing where we test points, like we did right here. See that, oh yeah, at -1, f is definitely the larger function, and at +1, g is definitely the larger function. But you can also see graphically that that is true. All right, yeah, definitely, good idea. Let's see, let's stop sharing, let's go back to the video. So then, to calculate this, so I would distribute this minus sign, so I would really write this as x cubed minus x squared minus 6x. So then we're going to integrate, and we're going to get, so the integral is x to the 4th over 4 minus x cubed over 3 minus 6x squared over 2 is just going to be 3x from -2 to 0. And the nice thing about these two integrals is that since we've subtracted in the opposite order here, we're just going to get the negative of what we got over here. So the integral of this will be negative x to the 4th over 4 plus x cubed over 3 plus 3x squared. Right? That's exactly what I'm getting. I'm getting minus x to the 4th over 4. I'm just doing it out of order to see that it's the same as this. Plus x cubed over 3 plus 6x squared over 2 from 0 to 3. And then we're going to add those together. So each of these separately should be positive, right? Because we subtracted them in the order so that they would count the area as being positive. So here's what I'm going to get. I'm going to plug in 0. When I plug in 0, each of those things is 0. So I get 0 minus whatever I get when I plug in -2. Plugging in -2 here, I get -2 to the 4th, which is 16 or 4. -2 cubed is -8. I get minus -8, so I get plus 8/3. And I get minus 3 times -2 squared is 4. Minus 3 times 4 is 12. Or I should say minus 3 times 4 is minus 12. This should be positive, whatever it ends up being. And it will be, unless I made some dumb mistake. Now we're going to plug in 3. So negative 3 to the 4th, you have to do the power first, right? It's not negative 3 parentheses to the 4th. It is negative 3 to the 4th. So I'm going to get negative 3 to the 4th, which is 81 over 4. Plus 3 cubed over 3 is just 3 squared. And then 3 times 3 squared is 27. Minus 0, 0, 0 is 0. And then we try and simplify. This is, again, where you probably should just use a calculator. So this is 4. So I get minus 4 minus 12 is negative 8 plus 8/3. Plus 9 plus 27 is 36. So I get 36 minus 81/4. And then you can, I'm a fraction kind of person. So I'm going to write this as 8 minus 8/3, but 8 is really 24/3 minus 8/3, right? Distributed the minus sign. And then 36 times 4 over 4. Let's see, 36 times 2 is 72, times another 2 is 144 over 4 times 81/4. Let's say I get 16/3. 144 minus 81 is 63/4. Again, calculator is probably wise to use here. And then we'd have to get the common denominator, so multiply this by 4 over 4, and you get 64 over 12. Multiply this by 3 over 3, and you get 189 over 12. And then you add it together, and you get 64 plus 189 is 253 over 12. The nice thing about this is you should be able to check this answer pretty easily, right? Actually, I don't know if there's a way to do this in Desmos or not. Yeah, I don't know. And now is probably not the best time to try and figure it out. Maybe if you have Desmos, there's certainly other graphing utilities that, if not Desmos, you can use to figure out the area interest. I do want to point out, though, that both of these were positive, right? This area was 16/3, which is positive. And this area was 63/4, which is also positive. So each of the separate intervals should give you a positive area that you're calculating, and you're just adding them together. The questions about this?
A quick question.
Yeah.
So I was on the -4, I think 4 squared all over 4, and then you go to -81/4 on the. Right.
So this is the negative x to the 4th over 4.
Yeah, I was just confused. How come you separated the negative sign? Because I've been doing it the other way, where I've been square, like for example,
like you'd be doing this.
Yeah.
So the reason that's not the case is because I've got minus x cubed. So so I'm just treating this kind of like itself, and the antiderivative of that is x to the 4th over 4. Okay. But it's minus x to the 4th over 4.
Gotcha. Okay.
And so when I plug in the 3 here, it's not right. It's not this. It's actually this, where you have to do the power and get 81, and then do the negative of that after. Yeah, it's a good question. Okay, so area between curves. It's a lot of this kind of stuff, where you're setting two things equal to each other and then trying to find out where they intersect. Sometimes they give you other things, but mostly it's that. Sometimes they do give you artificial limits of integration. So if there are other area questions you'd like me to address, maybe send me a message or start a discussion on Canvas, and I can definitely make a couple short videos if there are other types of area questions you have, or other questions in general, but specifically speaking to area. So let's go ahead and look at some volume stuff. And I'm assuming, so Nicole, just to be specifically sure, I'm guessing that's y equal to 4 minus 3 halves times x, right? It's not over x, it is 3 over 2 times x. Is that correct?
Yeah.
Okay. We've got y equals 0 to, okay, and we've got between. So these are the 4 curves bounding our region. So we need to, so I think for these ones, at least in the beginning, it's really to our advantage to draw the region. So most of these are pretty easy. Y equals 0 is just the x-axis. Right, there's y equals 0. X equals 0 is just the y-axis. X equals 1 is the vertical line. And what, so this is the only one that's actually kind of some work. Y equals 4 minus 3 halves x is the curve that has a y, or a straight line really, right? And so my graph is not going to be to scale because it's kind of do this big, but it's going to do something like this. So if I plugged in 0 for x, I would get y equal to 4. And if I plugged in 1 for x, I get 4 minus 3 halves, which is like 2.5. So it'd be a little bit lower. I'm not going to do it super precise and just be like, okay, and that's going to be something like that. And so when they're asking you to find a region, it can be a little bit misleading sometimes. If we weren't being super careful, we might accidentally, incorrectly, think that this was the region. I mean, it's got all the functions we're talking about. It's bounded by functions we were talking about, right? The boundaries are x equals 1, y equals 0, and y equals 4 minus 3 halves x. Here's the thing though, if they're saying your region is bounded by all these curves, then each of these curves has to get used. And for this blue region here that I've selected falsely, x equals 0 is not one of the boundaries, right? This line here, x equals 0, isn't one of the sides of that shape, of that region. So we know that's not correct. We know it actually needs to be, use a different color here, choose green. It actually needs to be this region here, because that region has each of these curves as one of its boundaries. So if they say something has to be bounded by all 4 curves, you need it to be bounded by all 4 curves. So then we're going to try and find the volume of the solid obtained by revolving this region. I'm assuming around the x-axis. Is that also correct?
Yeah.
Okay. You can also do the y-axis, but it's typically in this class I don't want to see. We don't always limit ourselves to the x-axis, but it is usually more true that we go around the x-axis. So I'm going to erase this right here because I don't really need it anymore. So what we're going to do is we're going to take this region and we're going to revolve it around the x-axis. And so here's the idea, is that, well, in fact, let me draw the shape and then we'll talk about the idea. So when I'm trying to draw the revolved shape, not that you have to draw it, but my idea is always just to take this shape and kind of reflect it in the axis you were revolving around. So I'm going to draw, this portion here, and I'm going to draw its reflection right there. And not that you have to, but then I'm going to try and kind of make it look 3D. So I'm going to do this, and then same kind of deal here. Right, so I don't know, it kind of looks like a piece of flan, as I imagine, right? Flan kind of sometimes comes like this, kind of jiggly on top, right? It's a piece of flan turned on its side. That's how I'm kind of seeing. And I'm trying to find this volume of the flan. So yeah, we can definitely look at that one for sure. So here's the real idea. What you're doing is you are going to be using what's called the disc or washer method. And really they're the same method. It's just that one of them has a little more, a few more pieces to it. What I always imagine is I'm taking so in this class, I believe we never talk about shell method. So whenever you're doing this, whatever axis you're rotating around, you're always going to draw a strip that is perpendicular to your axis. So if you're going around the x-axis, you're always going to draw a vertical strip. And here's what happens when I rotate that strip. When I rotate that strip around my x-axis, well, it's going to kind of do this. And the shape I get is a disc. So when I rotate this, I really get this kind of shape here. And I want to find the volume of that disk. Well, that's not too terrible because it's really just a circle with some thickness. So the volume of this disk is just the area of the circle times the thickness or the width. Well, that's not too terrible. We know the area of a circle. That's pi times the radius squared. And the width of this disk, well, again, I'm thinking of the width as being some small change in x, which I usually call dx. There's my width. There's my area. Now here's the thing. The radius of this disk, the radius is just whatever the height of my strip is. But the height of the strip changes, right? The height of the strip over here is 4. The height of the strip over here is 4 minus 3 halves times 1, which is 2.5, or 7 halves. 7 halves? No, 5 halves. Sorry. But the point is that the radius of our circle here is a function of x. It depends on where we are in the interval. So if I'm trying to write the volume of my disk, it's going to be pi times my radius, but the radius is just a function, 4 minus 3 halves x squared times dx. So that's the volume of just one disk located at x. But I don't want to find the volume of just one disk. I want to find the volume of the entire shape. Meaning what I'm really going to do is I'm going to add up all the disks. So there's like a big disk over here. There's a little disk over here. Right, and the idea is I'm going to add up all the disks, aka I'm going to integrate to add up all the disks to find the volume. So go to the other side here. So if the volume of my disk is equal to pi times my radius, which was 4 minus 3 halves x squared dx, is given by that, then the total volume, I don't know why I'm writing volume, I just usually write capital V. Oh, I know, I was going to write it. The total volume is where I'm adding up, meaning integrating all of those areas. Or all of those small volumes, I should say. And I'm adding up from as far left as x equals 0 to as far right as x equals 1. So that's how we set up the integral to find the volume, right? We are adding up all the areas of the disk. So we're integrating from x equals 0 to x equals 1 of pi times the radius squared dx. And then the rest of it is well, I don't want to say, is sometimes not too terrible. So what we're going to do is I always bring this pi out in front. So it's pi times the interval from 0 to 1. And I'm going to multiply this out. You could do a u sub here. It's not super necessary, though, because it's only squared. If it was like 4 minus 3x to the 5th, I'd probably do a u sub. But here I'm just going to multiply that and get 16. Let's see, 4 times negative 3 halves is negative 6. Twice is negative 12x. Plus negative 3 halves times negative 3 halves is positive 9/4 x squared dx. Yeah, that looks right, right? Yeah, that seems right. And then we integrate. We get pi times 16x minus 12x squared over 2. Just 6x squared, plus 9/4 x cubed over 3. The over 3 and the 9 cancel and give me plus 3/4 x cubed from 0 to 1. 0 to 1 are kind of the best limits of integration ever because you just plug in 1 and you get all your coefficients, and you plug in 0 and you usually get, I should say, the best if you just have powers of x because you plug in 1 and you just get the coefficients, and you plug in 0 and you get nothing. If you have other functions, you have to be a little more careful. So here I'm just going to get pi times 16 minus 6 plus 3/4, which is what, 10 plus 3/4. So pi times 10 plus 3/4, which is 10.75, or 43/4 times pi if you prefer. That's so that's the real idea there, is that you're doing this thing. So let's do more examples. Sure. Sure. Oh yeah, this is looking crazy. All right. So let's look at. I'm gonna do a slightly different problem, Abby, but it'll still be similar, because I have some different numbers I want to look at. But yes. So let me do. Let's do one other disk method example, because I think your example or your question, Abby, is actually a washer method example. So I want to kind of do another disk method so that we can contrast between disk and washer. And before I go ahead, also just to point out, for those of you in Merck's class, I don't think you've talked about these volumes yet. You will talk about them, or unless I'm wrong. Correct me if I'm wrong, but I don't think you've talked about volumes like this yet. You will eventually, so don't worry that I'm wasting your time right now. You will definitely get to see this at some point, or if you don't, you'll definitely use it in 16C. But you should cover this. It's definitely part of the syllabus. People just do things out of order sometimes, and I'm not sure who's out of order here. So let's do another one. Let's find the, let's see what I want to do. Sure, find the volume. Oh, I know. Sorry, I meant to ask one other thing. Are you guys rotating around the y-axis at all, or is it just around the x-axis or horizontal lines? Has anybody done revolving around the y-axis? Y, okay. All right, then we should do a y one. So let's do this. Sure. Sorry, I got to think for 1 minute here. Yeah, let's not make it terrible, James. Let's find the volume of the region of the solid. Writing these out is always kind of a pain. Find the volume of the solid obtained by revolving the region bounded by x equal to 0, y equal to x squared, and what do I want to do for that last part there? I don't want to use washer yet, so I just need to be smart. And y equal to 9 about the y-axis. For most of these volumes, you're probably going to need to draw the region. Desmos is great. I would certainly encourage you to use Desmos. This one's not too terrible to draw, so I'm just going to draw it. So here's my y equals x squared. Here's x equals 0, the vertical y-axis, and y equals 9. There we go, right there. And so actually, I was not specific enough. I need to be slightly more specific because technically it could be this region on the left because I didn't say anything else. So I should say the region in the first quadrant bounded by x equals 0, y equals x squared, and y equals 9. So I don't want this left side over here. Okay. So here's my region. And I'm revolving around the y-axis now. So whatever axis you're revolving around, I think this is really kind of important to know, you need to think of drawing a strip, as I like to call it, that is perpendicular to the axis. So I need a horizontal strip since I'm going around a vertical axis. And all I'm really doing when I'm imagining rotating this around that axis is I'm imagining this rectangle rotating around and becoming a disk. So, right. And the volume of that disk is exactly pi times the radius squared times the thickness, which is a small change in y. So a dy instead of a dx. And the radius here is just whatever this width is. But as you can see, the radius of the disk or the length of this strip depends on where I draw the strip. If I draw it lower, it's a shorter radius. If I draw it higher, it's a larger radius, meaning the radius is a function of my variable, right? It's not just some constant value unless literally the function here is a constant. So the radius has to be my function. But the thing is, my radius can't be y equals x squared. You can't just plug in x squared there because you're going to be integrating with respect to y. So if you're doing a horizontal strip where you're integrating with respect to y, instead of writing y as a function of x, you have to re-express this so that x is some function of y. In this case, square rooting both sides, you get x is the square root of y. And that's what's going to go here, not this. I mean, it's still the same function, you just have to solve for x as a function of y. So here, the volume of my disk is pi times the square root of y squared. And so then my total volume is equal to the integral of this area, or volume I should really say, pi times the square root of y squared dy. From how low can my disks go? Well, they can go as low as y equals 0. How high can my disks or my strips go? Well, they can go as high as y equals 9. So that's how we set that up. And then solving this one is pretty straightforward, right? Because square root of y squared is just y. So you get pi into the interval from 0 to 9 of y dy. You get pi times interval of y. That's y squared over 2 from 0 to 9. Plugging in 9, you get 81 over 2 times pi. So you get 81 pi over 2. Minus plugging in 0 gives you 0. So you just get that. So that's how you go around the y-axis. Again, I'm really big on this idea of drawing a strip that is perpendicular to your axis of rotation. So these are disk methods, and I would say, so you're always using the disk method if your region is flush with your axis of rotation, meaning there's no gap. Or I should say really meaning that the axis of rotation is one of the boundaries that is bounding your region. The answer is 81 pi over 2. Whereas the washer method, which we'll talk about next, is your region is not going to be right up against your axis of rotation, or your axis of rotation will not be one of the boundaries. So let's take a look at what have I got in mind. I got something. I like my notes. So let me see here. So let's find the volume. Volume of the solid obtained by revolving the region. I should write it. Solid obtained by revolving region bounded by what have I got here? Y equal to x minus 2. Do I really want that? That seems kind of funky now that I think about it. So let me think for 1 sec. No, that's dumb. That's not what I really want. I'm going to do this by y equal to x squared and y equal to 8 minus x squared. Is that too easy? No. Around the x-axis. So I know what these functions look like. Y equals x squared is everyone's favorite parabola. And y equal to 8 minus x squared is a downward opening parabola that has been shifted up 8. So it looks something like this. So I'm talking about this region, which is definitely not flush with the axis of rotation being the x-axis. So I need to do a couple things. I need to find where they intersect, so I'll have limits of integration. So points of intersection. Set these two functions equal to each other. Add x squared. And usually subtract 8, but in this case we can just divide by 2. And you could do x squared minus 4 equals 0 in factor, or you could just say x equals plus or minus 2. So whatever my interval is, I know it's going to be the interval from -2 to 2. And I think I want to draw more pictures. So these are going to be limits of integration. Our volume is going to be some interval from -2 to 2 of some stuff, which we'll figure out on the other side of the board. Okay, so let's draw that picture again. So again, what I'm really looking at, so if I revolve this, and actually let's cut off the parts we don't need here. So if I was going to revolve this around the x-axis, I'd have some sort of weird like donut-looking thing, right? If you can imagine this kind of revolving around, I don't really care about that so much as what happens to my strip. So I'm going to draw a vertical strip. And we'll think about what happens when I revolve that around the x-axis. So if I do that, here's the shape I'm going to get. Let me make sure I don't draw this wrong. Oh gosh, come on, James. Try and draw that a little bit better. So I should have some symmetry here. Sorry, one sec. Let me make this a little better. Okay. And then so we're going to go like that. Like that. A little bit of thickness. But then we've also got this inner part, right, that there isn't actually any of. So we've got kind of this. So we have a disc, a washer, right, where you've got this circle, but you've got the inner circle taken out of it. And we're trying to find the volume of this washer. Well, that's not too hard. It's the area of that shape times the thickness. So that's area times the thickness, which is just dx, right? Some small change in x. That's what this is. This is dx. And the area of the shape is the area of the big circle minus the area of the little circle. So I usually write this as pi times big R squared minus pi times little r squared, where there's your big radius, which is the function that's further away from the axis of rotation. Function further from axis of rotation. Notice I said axis of rotation, not the x-axis, right? Because sometimes the axis of rotation is some other axis if we're doing that. And the little radius, little r, is just the function that's closer. Right, so that's the function closer to the axis of rotation. So in this case, this is going to equal, so let's see, my function further from the axis of rotation was 8 minus x squared. My function closer to the axis of rotation was just x squared. So that is the volume of this washer, this small slice of the entire thing, which I can try and draw the whole thing, but it's probably not going to look very good. If I try to draw the whole thing here, let's see if I can do it. So let's see here. Here's my top piece. Here's my bottom piece, and I'm going to flip it over. I'm drawing the insides dash because I know they're going to kind of cover it up. And then it kind of does this. It's weird. Yeah, my picture is not great. Sorry. Yeah, that doesn't really help me see it. Yeah, sorry guys. Sometimes my pictures are not going to be excellent. That's just life. Yeah, I don't know. It's kind of like a ball shape with some like part of it cut out in the middle. But I could have done a better job probably. Anyway, don't worry about drawing the volume if you don't have to. So the total volume is going to be given by the integral of this. I'm always going to factor out the pi. So I've got 8 minus x squared squared minus x squared squared dx from -2 to 2, because those were the limits of integration we found earlier. And then usually these washer method ones are kind of numerically gross. If we want to find this, we have to multiply it out. So going back to the other side. So I've got the integral from -2 to 2 of 8 minus x squared squared minus x squared squared dx times pi. It's easy to accidentally drop the pi. So make sure you don't. We got pi times, let's see, so multiplying this out. 8 minus x squared squared is 64 minus 16x squared plus x to the 4th minus x to the 4th. That's convenient. Those cancel. That works out nicely. And then you get pi times, let's see. So integral of that is, well, I should say something here. So I should point out, because it's a little bit of a time saver, and or you might see this in the solutions manual, is that 64 minus 16x squared is an even function. So I could, and since I'm going from negative number to the same positive number, I could rewrite this as 2 times the integral from 0 to 2 of 64 minus 16x squared. So if you ever have an even function, it means it's the same on the right side of the axis as it is on the left side of the axis. Instead of doing the integral from -2 to 2 or -7 to 7 or negative whatever to positive whatever, you can say, well, I'm just going to do half the integral and then double it, which is going to be the same since both sides are equal to each other. So that's something you're always allowed to do. And it makes it a little bit nicer. I'll kind of show you how it would look if we done this way. So I'm going to get 2 pi times, and integrate this. I'm going to get 64x minus 16x cubed over 3 from 0 to 2. I'm just going to plug in. When I plug in 2, I'm going to get 2 pi times 64 times 2 is 128 minus 16 times 2 cubed is 16 times 8, which is also 128. And then when I plug in 0, I would just get 0. So I get 2 pi times. Now, instead of trying to do the hard math here, I'm going to factor out 128. Factor out 128, I get left with 1. Factor out 128, I'm left with 1/3. I think it's much easier to calculate 1 minus 1/3 than it is to calculate 128 minus 128 thirds. So I end up with 2 times 128 is 256 pi. 1 minus 1/3 is 2/3. 2 times 256 is 512 pi over 3. If you hadn't done this thing where you doubled it and went from 0 to 2, it gets a little bit grosser. Right, instead of this, you have, I would have, right, the integral from -2 to 2, so then I would have pi times 64x minus 16x cubed over 3 from -2 to 2. You plug in the 2, you still get the same thing, but then you get minus, you plug in the -2, and it's kind of the rest of it. How do I know it's an even function? That's a good question. This function, so polynomials are easy to tell they're even functions. So if you just have powers of x added together, then we know it's an even function if all the powers are even. So f of x equal to x to the 6th minus 2x to the 4th plus 3x squared is definitely an even function because it's a polynomial where all the powers are even. F of x equal to 2x to the 7th plus x to the 5th minus x is an odd function because all the powers are odd. Again, it only works for polynomials though. If you have other types of functions, it's not so straightforward. The way you really check to see if it's even is you check that f of negative x is equal to f of x. So here if I plug in negative x, nothing's going to change because negative x to an even power is just going to be changed into positive x to that power, right? Here if I look at f of negative x, I get negative x to the 6th, which is just x to the 6th. I get minus 2 times negative x to the 4th, which is minus 2x to the 4th. And I get 3 times negative x squared, which is just 3x squared. It's the same. On the other hand, odd functions, f of negative x is equal to negative f of x. In this case, right, f of negative x is 2 times negative x to the 7th plus negative x to the 5th minus negative x. That's going to change the sign. That's going to be negative 2x to the 7th minus x to the 5th plus x, which is definitely equal to the negative of this function. So that's what it means to be an odd function. And that's how you check in general. So actually a good kind of question to go along with that is, what's the integral from -6 to 6 of x to the 6th plus 1 over the square root of x cubed plus 8? Not x cubed plus 8. Square root of, might be a little bit careful here. Let's do it this way. Let's do x cubed plus x over the square root of x to the 8th plus 1. And so here's the idea here. So this function, by the way, here's the enrollment form one more time. Make sure everybody please do it. So this function looks really, really hard to integrate. I have no idea how it actually integrates. If you see something that looks really, really complicated, and you also notice that the limits of integration are opposite numbers of each other, there's a good chance that that's an odd function. Let's check. So is our function odd? So f of x is this function here. F of negative x is, let's see, negative x cubed plus negative x all over the square root of negative x to the 8th plus 1. Negative powers end up keeping the negative sign, or sorry, odd powers end up keeping the negative sign, even powers end up losing it. So I end up with, let's see, negative x cubed minus x all over the square root of just, this is still x to the 8th plus 1. And I notice, hey, look, this is equal to the negative of this. Because when you have a negative of a fraction, you only distribute the negative to either the top or the bottom, but not both. Because really, this negative here is -1, which is -1/1. So the -1 multiplies the top, the +1 multiplies the bottom. And that's exactly the same as this. Since this is an odd function, the integral from negative number to positive number of an odd function is equal to 0. And the reason why is because it's an odd function, basically it's positive on one side and negative on the other. So you've got something like, I don't know exactly what, but like if I plugged in, it's dumb. I plug in 0, so this does something like this probably. I don't know exactly, but maybe it looks, you know what? We have a graphing tool at our disposal. Let's go ahead and look at that. So one more time here, let me show my screen. I should actually grab Desmos maybe. Let's close that, close that. So if I graph this thing, which is x cubed plus x divided by square root of x to the 8th plus 1. Let me zoom in a little bit. So you can see that between -6 and 6, right, from here to here, all this area is negative, and from here to here, all this area is positive, and they're exactly canceling each other out because of the symmetry of being an odd function. So since the function's odd, this positive area here exactly cancels out with this negative area over here. So if you're integrating from -6 to 6, or -4 to 4, or -3 to 3, right, as long as it's a negative number to the same positive number of an odd function, the area cancels out. If it's an even function, the area doubles. So if we look back at our other example, the one that I don't remember anymore, let's go back. It was on the, no, I totally erased it. It was something like, but not exactly like 16, I don't remember. Sorry, I lost it. It was, let's just make up numbers. Let's say it was 16 minus x squared. That's not where I need to put that, sorry. Right, if you look at this, instead of integrating from -4 to 4 or -2 to 2 and getting all this area, you can just go from 0 to 4, get half the area, and then double it because of the symmetry on either side. So totally works for even functions to do that, for odd functions to say it cancels out. So the point is that if you see something that looks gross and you see limits of integration that are opposites of each other, there's a good chance it's an odd function, and you might want to check that to see if the answer is just equal to 0. Okay, let's see here. Where'd you go? There we are. So I should ask, I know we spent most of the day talking about area and volume, which is fine. Is there anyone from the MERCS side of things that has any questions about what you guys have been doing? If not, that's fine. I just wanted to check in with you guys. Thursday, we can definitely spend more time going back the other way. Let's do another disk or washer method question. So I should mention, most people eventually come to think of the disk and the washer method as being the same. The disk method is the washer method. It's just you're not taking out any inner part. Or you can say the disk method is the washer method where the inner radius is 0. So they're really kind of the same method eventually. Yeah, we can definitely do a partial fractions example. So since I don't want to, I'm just going to make one up. The numbers might be gross. It's fine. I don't exactly know what you guys know with partial fractions, so we will try to make one up. It's not too terrible. Let's do this. Let's do the integral of, sure. X plus 1 over x times x minus 1 squared. I'm assuming you guys are doing repeated linear factors. Is that correct? I'm going to start with a slightly easier example since I'm not hearing anything. So let's just do this one, the integral of x plus 1 over x times x minus 1. So you might think to try u substitution here, and although it's not, and it's something I always look for just in case, it's not going to work out nicely here. It's not entirely true. You could do a u sub with the back sub. If you think of this bottom as being x squared minus x, you might think, well, du is 2x minus 1. That looks like you could almost get there, but not quite. So if it's not perfect, I just kind of ignore it. So we're going to use partial fractions. And partial fractions is a method of integration that you can use if you have two things, well, 2.5 things, 3 things that are true. You have to have a rational function, meaning it's a polynomial divided by a polynomial, and it has to have the degree on the top has to be strictly less than the degree on the bottom. Has to be true to be able to use partial fractions. If it's not, if the degree on top is bigger than or equal to the degree on the bottom, then you can fix it by doing polynomial division. The second thing that has to be true is you have to be able to factor the denominator. If you can't factor the denominator in some meaningful way, you cannot use partial fractions. Here, the denominator is already factored for us. Most of partial fractions is just algebra. So here's what we're going to do. We're going to say that our integrand, x plus 1 over x times x minus 1, can be written as 2 fractions with denominators x and x minus 1, where we don't know the numerators. And the reason this is true is because if you were adding these 2 fractions together, you would exactly multiply this one by x minus 1 over x minus 1, and this one by x over x, to get the common denominator x times x minus 1. So if you have a denominator that can be factored into different parts, you can express that fraction as a sum of fractions with those separate denominators. And in fact, the way we figure out what the numerators are by going backwards and saying, oh, I'm going to multiply this by x minus 1 over x minus 1, and this by x over x. So here's what I get. You get x plus 1 over x times x minus 1 equals a times x minus 1 over x times x minus 1 plus b times x over x times x minus 1. And then we completely ignore the denominators. In fact, usually what people actually do is they just multiply both sides by this denominator. So really, what people actually do is they say, oh, x plus 1 equals a times x minus 1 plus b times x. Right, we ignore the denominators. So people often think of just taking this whole equation and multiplying it by the common denominator. So that this cancels out. Then when you multiply here, the x's cancel and you get x minus 1 times a. And when you multiply here, the x minus 1's cancel and you get x times b. Just make it heavier. And then our job is to solve for a and b. So now we gotta go to the other side. Now there's a couple things to keep in mind when solving for a and b. This example is a fairly straightforward example because all of the factors are non-repeated linear factors. So I've got this. Sorry, I was looking back here for a reason. I've got x plus 1 equal to a times x minus 1 plus b times x. And the first plan of attack, when you're trying to solve for a, b, whatever, is to pick convenient values of x, meaning pick values of x that make one of the pieces 0. So I'm going to pick x equal to 1, because x equal to 1 makes this part 0. So plugging in x equal to 1, I get 1 plus 1 equals a times 1 minus 0 plus b times 1. So 2 equals b. Great. And I'm going to pick the value of x that makes this part 0. So I'm going to pick x equal to 0. 0 plus 1 equals a times 0 minus 1 plus b times 0. So I get 1 equals a times negative 1. So multiply both sides by negative 1, I get negative 1 equal to a. So then, here's what we've done. We've said, okay, our fraction, x plus 1 over x times x minus 1, equal to a over x plus b over x minus 1. Well, we've actually found a and b. So x plus 1 over x times x minus 1 is equal to negative 1 over x plus 2 over x minus 1. And the reason we were doing this is because we were trying to integrate this thing. So I'm using a little bit of room here. So I can say the integral of this is equal to the integral of this. With some dx's, of course. And then we can integrate each of those pieces really straightforwardly. A lot of the time with these, you're going to have logs. So the integral of negative 1 over x is just negative. The integral of 1 over x is the natural log of the absolute value of x plus the integral of 2 times 1 over x minus 1 over x. I give this as 2 times 1 over x minus 1 is just 2 times the integral of 1 over x minus 1, which is the natural log of the absolute value of x minus 1. So that's how you do a relatively easy partial fractions question. They do get more complicated. We can do, yeah, we got time. We'll do one more real quick. So one way they can get more complicated is if you have a repeated linear factor, like x plus 1 over x times x minus 1 squared. I'm just going to run through this quickly, and then we'll call it a day. You guys should definitely think about what kind of things you want me to talk about on Thursday, and if there's any short videos you would like me to make in between now and then, because I will try to, if you let me know. So let's see, here we're going to set up the partial fraction decomposition, which is just the algebra part. We're going to have x plus 1 over x times x minus 1 squared equal to, so now we have to break this up actually into 3 pieces. You've got a over x. And when you have some factor that's to a higher power like this, you have to have that power and all the lower powers down to 1. So I need b over x minus 1 to the first and c over x minus 1 squared. If this was x minus 1 to the fourth, I would need b over x minus 1, c over x minus 1 squared, d over x minus 1 cubed, and e over x minus 1 to the fourth. You need all the lower powers up to the power that you have. And then we're going to do the same sort of thing we did last time. We're going to multiply everything by that denominator. When you multiply it on the left, it just cancels out, and you just get x plus 1, or whatever your numerator is. When I multiply it here, the x's cancel. You get a times x minus 1 squared. When you multiply it here, one of the x minus 1s cancel. So you get b times x minus 1. When we multiply here, the x minus 1 squareds cancel, and you get c times x. We're still going to try and solve for a, b, and c the same way we did previously by picking what I like to call convenient values of x. So I'm going to pick values of x that make some of these things 0. I'm going to pick x equal to 0. On the left, I get 0 plus 1. On the right, I get a times negative 1 squared plus b times 0 is 0 plus c times 0 is 0. So I just get this. So a equals 1. And then I'm going to pick x equal to 1, because that makes lots of things 0. If I do that, I get 1 plus 1 on the left equal to a times 0 plus b times 0 plus c times 1. So c equals 2. But then, and this is always the case with repeated linear factors, you always have, you never have enough convenient values of x to pick. There's always going to be one of these things at least where you can't just say plug in x equal to something and get everything else being 0. So once you've exhausted all the convenient values, you have two different choices. One choice, which is not my choice, is to pick some other value of x. You can pick x equal to 2. In fact, I will do it. I pick x equal to 2. I would get 3 on the left equal to a, which is 1, times 2 minus 1 squared is just 1, plus b, which I don't know yet, times 2 times 1, plus c times 2. So I'd end up solving for b, right? I have 3 equal to 1 plus 2b plus 4. So I get 3 equal to 5 plus 2b. 3 minus 5 is negative 2 equal to 2b. B is negative 1. This is not my preferred way of doing it, although it totally works fine as long as you only have one more thing to find. If you have more than one more thing to find, it's usually kind of a giant pain. What I prefer is the method of what's called equating coefficients. And I know we're over time. I'm just going to finish this, and then I'll leave you guys with it. So I like to look for the highest power of x on either side. If I multiplied this out, I would have an x squared. So if I think about the power or the coefficient of x squared, well, on the left-hand side of this equation, I have no x squared. On the right-hand side of this equation, if I multiply this out, this would be a times x squared minus 2x plus 1. So I would have an a times x squared. And if I multiply this out, I would have b times x squared minus x. So I would have a b times x squared. And I would have no c times x squared. So here's what I can say. I have 0x squared on the left. I have a plus b x squared on the right. And the amount of x squared on the left has to be the same as the amount of x squared on the right. That's the only way polynomials are actually equal to each other. So a plus b has to equal 0. Knowing that a equals 1 means b has to equal negative 1. So that's another way you can figure out what b is, which I think is more convenient. I will leave it at that. Well, I won't quite do that. So then we would plug back in a, b, and c, and then integrate that to figure out what the actual interval is. So I should finish that because we're so close to being done with it anyway. Let's go ahead and finish it off. So here's what we've got. Sorry, I know we're a little over. You're welcome to go if you need to go. I totally understand. Always true, right? If class is over, I mean, you're welcome to leave anytime. If class is over, you're welcome to definitely leave. So here's what we've got. We've got this x plus 1 over x times x minus 1 squared equal to a over x, a was 1, plus b over x minus 1, b was negative 1, plus c, which I think was 2, yeah, over x minus 1 squared. And then we were trying to integrate this, so we're really integrating all of this. And we're going to end up with the natural log of the absolute value of x minus the natural log of the absolute value of x minus 1 plus the integral of this 2 times x minus 1 to the negative 2 is 2 times x minus 1 to the negative 2 plus 1 divided by negative 2 plus 1. I'm just using the reverse power rule, and I'm not worrying about the fact that it's x minus 1 because you do a quick substitution there. So we end up getting this, which I'm going to write as negative 2 over x minus 1. So that's how you would finish that problem off. Sorry if that was a little quick, but I did want to get that for you there. We can definitely talk more about this on Thursday, or if you have other partial fractions, things you want me to address, I'm happy to make a couple little videos. But I should definitely end class there. So I'll see you guys later. Take care, and you know how to get a hold of me. Talk to you later.